So we are about to start with our second. We finished with contributed papers, and we are about to start with our second invited talk, a keynote lecture actually, by Uwe Zdun from the Technical University of Wien. I know Uwe mainly through his contribution to patterns, and there will be some patterns here as well. But what got me interested in this talk is conformance. Conformance is a very important topic. My PhD student does some work in automotive industry related to this, but I think this is a more broad topic. And without further hesitation, I would leave floor to Uwe.
Okay, Valentino, thanks a lot. So is it loud enough, the microphone? Or can you hear me? Okay, perfect. So I like to talk about conformance assessment and detection strategies for or in microservice architectures, assuming to a certain extent that these microservice architectures are used in a continuously delivered fashion, like in CI/CD, the current DevOps practices, for which microservice architectures today also the de facto standard architecture that is usually used for a couple of reasons. I hope you are all somehow familiar with microservice architectures. I introduced them a little bit during this talk as well. But let's start first with the challenges, and here we start with a little definition of microservice architectures. Let's say a typical definition would let them be described as consisting of independently deployable services that are changeable and scalable in a certain way, usually not so micro as the microservice suggests, usually something that one team can build, sometimes a bit larger team even, but important, each having a single responsibility in a larger scale system. So this can be a system with just 3 services and they have 3 main responsibilities in the business. This can be a system with thousands of responsibilities that are in thousands of such services. Some are a bit larger, some are a bit smaller, usually modeled after business capabilities, so things that your organization cares about. Yeah? So if it is an ordering system, the order management would be one typical function that is in one microservice as an example. So they are nowadays coming with a couple of technologies and patterns that are actually employed. For instance, typically microservices are today deployed in lightweight virtualization containers or some other virtualization technology. So containers are being probably the most popular one, but you also have function as a service as another deployment architecture. They encapsulate their own state, communicate with message-based remote APIs, usually in asynchronous fashion, and that leads to a rather loosely coupled architecture. Another point about microservices that is very interesting and important is that they usually have polyglot programming and persistence and also technology stacks, meaning that if you have more than one such microservices in your architecture, it is quite common that actually the different microservices use various technologies, like a different database technology per microservice, a different kind of schema model that you apply, a different programming language maybe, a different technology stack lying underneath, for instance, how you do the monitoring, how you do the communication, and so on. Meaning you need to deal with all of this in your organization somehow. And last but not least on this list here is that a very important characteristic is that they usually employ all the common DevOps practices that we see today and that have changed our industry quite tremendously, together with cloud-native development and things like that, and meaning that actually we go away from releases that are like every year or every second year or something like this, to actually being able to deploy your software system on a weekly, hourly, daily basis, something like this. So in the extreme case, every single commit that goes into the repository is actually committed. Yeah, last point here is end-to-end monitoring. So such a system, of course, needs to be observed. You need to know what is going on. And that's another key characteristic. So if you compare this to the monolith, which is typically discussed here as the contrast, so it's a very microservice kind of terminology that you compare monoliths to microservices, we see the following situation. So we have something like this here as a monolithic application, which is very often the starting point. And it's also recommended to be the starting point sometimes. So we have something like we have a couple of services which are somehow connected to each other. In this case, these are components all in one process, usually, that can run on one machine, for instance. There's one big database for the whole system, and there maybe is an application UI if it is nicely structured like this. And you have a typical three-tier architecture: database, business logic, UI. In contrast, the microservice architecture, these components here are usually broken down into these services. In this case, we have 4 backend services and 2 front-end services. The client is usually shielded by an API gateway that hosts the application API, where all the externally visible functions are located. These are then connected to these front-end services that actually manage this. This can be structured a bit differently, but this is a pretty typical architecture. And then somehow these services here communicate in a loosely coupled fashion. Here they do it via a message broker that is actually taking events that are in asynchronous fashion, for instance, with messaging sent to the message broker. The message broker sends the events to the recipients. Maybe it's a pub-sub architecture that is even a bit more loosely coupled, and so on and so forth. And here you see that each service also has its own data store, meaning that they really can be independently developed, and that's one of the main goals of this kind of architecture. Now, in this small-scale example, if these components are not too large, let's say, this actually doesn't matter much if you have a modular monolith for many properties or a microservice architecture. And in many aspects, the microservice architecture is much more complex, and you shouldn't go to it. So if you have a small-scale system. But if you're growing large-scale and have a lot of teams, what tends to be the case in the industry is that these systems turn at some point into spaghetti monsters, where it's even impossible to distinguish these components anymore. So, then change is almost impossible. Business changes take weeks or years to be actually released to customers. Many errors happen, and things, and so on and so forth. So you see that there are many motivations why you introduce microservice architectures, but where they really shine is actually when you're going large scale, when you have big systems. Here's an example, for instance, by Uber's microservice architecture. And Uber has nowadays deployed, is actually already some years old, but has deployed something like 2,200 critical services. So it's not a small scale. And you don't need to look at all the 2,200 services and how they interact all the time. They are, of course, in certain compartments. They work together with some services. But still, to manage such an architecture is quite difficult, And to understand, have they all these teams of the 2,200 services employed the best practices that you in your organization want to see in this microservice architecture? Is this really the case? Is first of all difficult, and more difficult than in a monolithic architecture where everybody uses the same programming language and the same technologies, all is on the same database. I hope that makes sense. And that's the kind of challenge we want to address here. And here's also written, so despite the many guidelines and best practices that are published about microservice systems, it is challenging to look at them in a comprehensive way, especially in such large-scale settings because of the size and complexity of the microservice system, the polyglot nature of them, and the continuous demand for evolution, so things are changing all the time. Yeah? And then another point here is the existing guidelines for practitioners are usually informal things. You find blog posts that your colleagues wrote. You have a pattern which is written in natural language text and things like that. And that is, of course, also not so easy. A little excursion here, how we usually do it, and some colleagues also in the industry do it, is that we try to identify architectural design decisions. So that is in software architecture an important concept nowadays. I think that has also gained significant traction in the industry. And here the idea is that you document the decisions you take in the system that have a long-term and significant influence on the system. So if you have a system like the systems I have mentioned before, you take a lot of decisions every day during development and programming. If you would record all of them, you would have a lot of documentation that nobody will ever read. Yeah? So if you are able somehow to, let's say, think about what is actually long-term and significant for your system and only document those, that is usually very beneficial for people coming onto the team, understanding the most significant things that actually happen in the system. Now, how can you define this or say where is the borderline? Yeah, like when should you document it or not? And here, the thing that is usually done by practitioners is to say the things that are really, really costly to change. Yeah? So if you say this costs us one man-day to change this, it doesn't make sense to be an architectural decision. Yeah. For instance, if you go from monolithic to microservice architecture, it costs millions of euros or even more. No? So that makes sense to document the exact reasons why you did this and so on. So and architecture is then seen today as a result of a series of such decisions. And you, as an architect, have the role to prioritize them, make a compromise between them, and then we get to all the qualities that we have in the architecture, because the qualities of the architecture, the non-functional requirements, are usually the things that you actually make decisions on. Yeah? So that's, let's say, a modern view on architecture today, as we also teach it. And now coming to a concrete example of an ADD that we use also as kind of running examples here through this talk. So mostly we give examples from the security of microservices in this talk. And here we have the authentication on passes from client UI or UIs to system services. So I have given you on the right-hand side for the picture we have seen before 2 examples, the red pass and the yellow pass. So you see the client over the API gateway just reaching a front-end service, and the front-end service can handle the thing that is asked for on its own. The request is handled by the front-end service is one possible path. Another possible path would, for instance, be that the client goes to the API gateway, goes to the front-end service. The front-end service raises an event, like, for instance, order is coming in. Then this event is managed here in the backend service. Maybe some database operations happen, and then I go back with a result of this to the client. That is another path. And now there can be many, many more paths, including, of course, all these combinations of services. So a possible path is, of course, also that I go down here. This service calls then this service service called this service, then I go back, and go back to the client, and so on. Yeah, for instance, an order service that needs shipping afterwards needs another service as a helper. No? Now, what is authentication on these passes? It is essentially that I look at each and every of these steps. So each red and each yellow step here, for instance, in these 2 passes, are they all authenticated correctly? And here authentication can happen with many techniques. And these are documented as patterns. Valentino mentioned patterns before. No? So, for instance, token-based authentication is one such pattern that can be employed, or protocol-based authentication. Another one is API keys, which is not so secure like the first two, but is still a valid authentication method in many cases. Plaintext authentication is an authentication, but it's not secure. Plaintext authentication over an encrypted protocol is okay to have, but it's not secure, but better than nothing, and so on and so forth. And no authentication is, of course, one issue. And the last option is authentication not required. So no authentication is the worst. No authentication required. You also need to consider, because sometimes you have public APIs where you don't need any authentication. Yeah, and this case also needs to be considered. And now you want to check through all of your systems in all of these passes. Is this actually a valid authentication method? And the case of security is interesting. What you actually want as conformance check here is 100% correctness usually, or conformance to the practice, because 99% secure is also insecure. It's better than, let's say, 5%, but still, if there is one hole in the whole system, it's a problem. That's not the case for every architectural design decision. So for instance, if you conform to layers 99%, then you're pretty good actually. No? So that's an interesting consideration. So the challenge here, which I wanted to bring across with this example and with the ADDs, is that to manually validate the conformance to the ADDs of microservice systems is very time-consuming and error-prone. And why did I use this example? Because these passes, if you think about the 2,200 services again, they lead to a combinatorial explosion. Yeah? So if you do this by hand for such a large-scale system, it's really tedious. And now you need to check this in a CI/CD situation for every commit that a developer does. Yeah? So that's a lot of work. No? And that nobody can do in a company. No? And here, of course, if you can automate things, that would be of tremendous help. No? And we also want measures for assessing these options if they are missing. Why measures? Because if I tell the manager to run all these checks on their own, or the developer is not very good, especially people at the higher levels like architects and in bigger companies, they also want to know how good we are, let's say, in all our 15 systems that we have deployed and things like that. And here measures are, of course, very helpful and metrics are needed. No? Okay, I mentioned the role of continuous delivery a couple of times. So this is interesting because microservices are likely to be delivered with CI/CD. But as I said, CI/CD can also help us here because we can actually run these checks automatically each time the delivery pipeline runs. And we can automate them completely. So that as a motivation, and now we come to our approach that we have employed in a couple of fields, and I basically talk about the things we did in microservices specifically, and then narrowed it down a bit to the security of microservice topic. So what we usually do, and here come in the patterns again and other best practices and the reusable architectural decisions, is to systematically search for them. So this is an interesting and important part of our research. So we think that it's very important to observe what is actually going on in practice, yeah? And try to put our research into a perspective where we actually do real work or things that are close to real work that are relevant best practices in the industry. For this, we usually do systematic studies of the gray literature. Sometimes we include also scientific literature if it's important here, and try to systematically mine these practices. Also bad smells, so practices that you should not employ, are things that we sometimes address here. And we have done this for quite a number of fields in this one area that we have seen here. For instance, we have done general patterns and practices on microservices. We have best practices and patterns on infrastructure as code, which is the automation of the setup of the infrastructure during deployment. Yeah, you use tools like Ansible or Terraform to actually set up the deployment, for instance, in the cloud or in a set of service. Service meshes are an important technology that is underlying these practices and the microservice architectures often as a deployment technology. Then microservice APIs is one of our recent foci where we really did a lot of work on different API patterns. It is so important because that is actually how the microservice system is visible to the outside world. So for a microservice architect, the API is very important usually. Then relations to domain-driven design, which is usually used for the design of these kind of systems. Security in the IAC field and the microservice world, also for the APIs in a sense, and last but not least, some CI and CD pipeline best practices. Okay, just to mention that we have studied this broadly and think this is really an important foundational step for this kind of research. I gave one more example. We had another example before in the ADD. Here, one from the API field, where we just have the look at the category of the API quality. And there you see that we have modeled in our book on API patterns here quite a number of such decisions. So the handling of reference data, the avoiding of unnecessary data transfer. So this is like how large your messages actually are. So sometimes you transfer too much information, for instance, that is bad for security, that is bad for bandwidth, that is bad for performance. But for some clients, that's very useful, and you want to make such decisions. Just to give a few examples. Here's one client identification and authentication at the API level that is actually also security related. What else do we have? Explicit specification of quality objectives, penalties, then the metering and charging for API consumption if you want actually to charge money or have a freemium account for your API. Things like that are often important. Rate limiting so that not anybody can abuse your API, which also has a security implication. And then preventing API clients from excessive usage would be this one, then communication of errors and explicit context representation. Just to give you an example how this could look like at a broader scale. So again, we had before one ADD here with a couple of possible practices that could then be described as patterns. And here we have a couple of such decisions and how they are related. So at the end, you get a pretty comprehensive design knowledge of a field. That's a goal. And now for those that are interesting for a company, it would be interesting to check conformance to those. But before we can do that, we actually need to extract the information from the system. And now we said that these systems are very polyglot and they are very different in their structure. So it might make sense to first model the system, so that we can extract the system from the source code or model it manually if you like. But for this, we must first be able to model it. So our first next step is usually to derive a modeling method for the field. For instance, microservice architectures, like the examples we have seen, we often model with so-called decomposition models, which is essentially component and connector models. So we have the components and the connectors in the system, like the service was connected to the API gateway and the database as an example. And these we try to model formally. Here is a bit of an example. You don't need to read it in detail, just to say that it's also there, more for the papers. And what we do in addition to the main elements that you know from UML component models is usually to have extensions which we model as stereotypes that explain the different things we actually want to check. In this case, of our security examples, we model important annotations for the security of the system. I give examples in a minute. Then we code this usually in our framework called Codable Models. That's a Python library for specifying such models in code in Python. And have a whole bunch of generation techniques here. Especially what we also generate is all the visualizations in UML with plant UML and similar libraries. So that we don't need to draw the models, but they are automatically generated for us. And if you make little changes, they are automatically drawn. So that's the idea here. Then we need to extract the model from the code. And here we have developed a new extraction approach. because we needed now to also deal with this polyglot nature. Yeah? So the typical way to extract things in most scientific works is to use a parser generator and generate a parser. And you might have spotted, if you look at such works, that they are very often mainly focused on Java. And in Java, only on a very specific subset of the language, which is most often used. Yeah? So for instance, if you want to know that two services interact with communication frameworks that are typically employed, that is usually not covered. If two services are communicating via the database, it's typically not covered. If two services communicate via reflection, it's not covered. So actually, many of the techniques that we see in service development are not covered by the typical architecture extraction approaches that we see. And so we come up with another approach, and this is only for Java. No? If you run, for instance, we tried one of the example actually that is in this slide, we tried, there are some JavaScript services, we tried the some recent JavaScript parsers, open source parsers. They actually did not extract the information correctly because the newest language features of JavaScript were not supported yet. So, and if you have more modern things that are not yet supported, like for instance, much of the information in microservice systems is like in a Terraform script or in, I don't know what else as new technology you employ, then you don't have any parser for it yet. No? So that might actually lead to problems. Okay, anyway, so what we came up with is a more modular approach to actually only extract the information we need, which is actually quite a small amount of information, and then we don't care actually if it is in the Java file or if it is, let's say, in the Docker Compose file, yeah? Because we just specify the lines we need, and we specify them quite generally. Yeah? So that's the idea. If you need to or want to know more about this, you probably need to read our paper because we don't have the time yet to go into much detail here. No? But we have done this for component and connector views and API models and deployment views and security features, and it worked quite well. And the interesting thing is, with this more specific specifications or more opportunistic specifications in a sense, we can also be more, let's say, accurate in the evolution of the systems, yeah? Because we look only at specific features and try to code them in a way that they actually survive evolution steps. Mostly, we either get a warning something went wrong here, or we get the situation that actually we are good and that works. Okay, let's look at a small case here, which is in standard robot shop. Which we use as one of like 10 cases we have as open source cases we regularly use. Here, of course, we don't get these super big, large-scale industrial systems all the time. But for instance, this case, it's done by 14 practitioners, is highly polyglot, has a lot of commits, and is not of big size, but also not so small. No? And the highly polyglot was very important in this case. For instance, you see that almost every service is done with a different technology, and they use tons of these different technologies. They use, in addition, like monitoring technologies and so on. Yeah? And we have extracted this model here. So this is the model by our extractor. We can zoom in a bit just to see one model as an example. This is also auto-generated here with PlantUML. No? And we see that this is, for instance, highlighted as a service here, or this is highlighted as a Redis database, which is a database component. We see also some security annotations here if you look very carefully. So for instance, you see that this HTTP2 connection is unencrypted. And you see that here is the annotation HTTP, which means that it's not HTTPS, so it's also unencrypted communication. It doesn't have many such annotations. Why? Because this system is not very secure. No? Another security thing that we see here, or security decision, is this one, that we have a monitoring for one of the services. End-to-end monitoring is also something that is usually recommended in the security guidelines. And actually, not much is monitored here, but at least this service is monitored. No? Not all is monitored, let's say. Okay. And now we come on to our next step, which is actually the conformance assessment. And here we want to quickly go through this to understand how this can work. I show a bit more details here, but I skip through them, and you would need to read the papers if you want to really understand how this works in detail. So what we do is actually, as a conformance extraction process, to extract the models and the traceability information, then do the detection of the conformance in the relation to the models. And here the extraction would get the source code. We could also directly input the models here if we have a model system, but we also get the traceability information, meaning we can trace back from a violation that we find to the source code elements that actually have caused it. Also, we have the system models to look at the models in addition, so what model elements are needed. And then we calculate metrics and indicators. So we have conformance violations in certain places, and then we can say how many violations we have overall compared to the elements in the system. And for these also we do traceability links and lists of the violations, and at the end we get these metrics and indicators that we actually provide. Okay, to do this, so now we are going into the scientific, let's say, part of it. So how do we come up with this? And then at the end I show the approach in use, which is more or less this approach. So this is the approach in use. But in order to specify this, what did we do? We actually went with security experts from companies through the security guidelines and our techniques, and they assessed what is good and what is not so good techniques. Yeah? So in this case, for instance, of our example, authentication on these client and service passes, everywhere token-based authentication and protocol-based authentication, one or both, but on every link we have them is good, no? Is very good. It's also okay, and that's the plus, the meaning of the plus, that you have token-based authentication, protocol-based authentication, API keys, or playtest over an encrypted protocols on all connectors. Yeah. So meaning that, for instance, some are on the not so secure API keys, but we have everything authenticated correctly. No? So what, for instance, happens is that the backend is authenticated with token-based, but you have API keys on the communication with clients to make it easier for clients to communicate, like public clients or something like this. So this is also considered acceptable practice, but is not like perfect, no? Like you using OAuth or something. And then there are different shades of gray which are not so nice. No? So like if you have only the large majority done with acceptable techniques, which is this one here, it is not good, but at least you're on the right way. No? And the last one is at least some connectors have something which is minus, is not good, it's bad, but at least you have started. No? And of course the worst thing is you have nothing. No? So that's the kind of shades of gray. This, for each of the systems we have then assessed as a ground truth with these security experts from the companies. Yeah? What we want is actually that we want our extracted models and want to see how they actually conform to these best practices as they have been defined. And lastly, we want to compute metrics and a statistical validation and say for each of our practices how well they are supported. Yeah? So, and the metrics are by purpose very, very simple. Yeah? So what we do is we have many metrics, and the metrics are always, let's say, go back here quickly, for one technique, like here, for instance, token-based or protocol-based authentication and so on, to essentially say we have one metric for it. For instance, this one is the authenticated connectors at all. And here then are the securely authenticated connectors, which is actually the connectors that are either token-based or protocol-based. Yeah? And so you see the and we divide them by all the connectors, or in this case, all the passes that we have. Yeah? So the passes are much more than the connectors. Okay. And these very simple metrics are, of course, a bit hard to interpret, yeah, because you have many of them, but they are very granular, yeah. So you can see where your problems are, and at the end you have such a large table for your systems. In total, we had 30 systems in our ground truth. One system that is the number 0 always, which is the actual system, and 2 variants of the systems we realized, yeah? According to things that are described in the literature as typical such practices. So now let's quickly look at our example system that we have seen, which is RS0, and we said it has almost no security practices. And if you go down, you see there's not much here, no? Especially here in this, I think this is the metric we have looked at. It is completely empty. Yeah? But for instance, it has some things on observation in the system. Yeah, that's it. Not much more. No? Secure connection, which is the first one, it also does not have. Yeah, and we did this for a couple of systems, and the first thing we then did is to calculate how well these single metrics actually predict using correlations. In this case, the Spearman correlation. The values. And you can see that some of these metrics, the single metrics, actually have already a very high correlation. Some have not such a good correlation, which leads us to the assumption that maybe we are able, or hypothesis, that maybe we are able to predict with these metrics the properties that we have here. Yeah? So is this a secure connection or something? To statistically analyze this, we used ordinal logistic regression. So the ordinal regression analysis we performed then led to different regression models. Interestingly here, we didn't use all the variables in the best models. So for instance here, a subset of the models is taken. And you can see that actually from these evaluation metrics, they are, in these cases here, this example case, perform quite decently, which they perform actually for all our cases that we analyzed somehow. And you see here the values that are interesting. The p-value is also calculated, but it's not so important in ordinal regression. Usually you use these c-indexes and the bias scores, and very often the bias-corrected, bootstrapped versions are most telling. Yeah, so you see they are lower than the original values, but still a very high c-index can be reached with very low bias score, which is good in this case. So now, in order to understand if it's then the plus or the minus, you actually need to interpret these intercepts here, which is a bit complicated. And so we try to make this a bit easier and come up with one value at the end of the day. Yeah? So which is actually a value ranging from this plus to this minus, where we have encoded these three values with numbers and then made a predictor for it. Yeah? So, and this we call a detection strategy because it's actually a metric-based rule, and that's how detection strategies have been defined in the literature. Before, but it's not like in the literature before a metric-based rule that is, let's say, handcrafted from different elements, but it's a statistically derived metric-based rule. So we can actually, for each of our properties that we had before, come up with two predictors here, which are commonly used in ordinal regression, means and fitted predictor, in order to come up with one value instead of these complicated, let's say, tables we had. And here we have applied this to four different similar ADDs, and you see in this data set that we reached then actually for each of our models. We have again three models, the three best models that we have found in the ordinal regression, and you see that they have a high Spearman correlation and rather low overall, mostly low mean squared error that they predict. Yeah, so that was a bit the interlude on details on the scientific approach. So what can we take away from this? If you see the approach in use in total, we take the source code, extract a model from it. Or we model the system directly as a model if we like modeling. But depends. No? So you need to invest a bit of money and time into having a source code extraction if you need it. If you are happy with just modeling it, you can do it by repeatedly modeling it as well. You can use or just use the approach on models. From this we detect metrics, and these go into the ordinal logistic regression. We create the regression models, and we apply our detection strategies and have then different predictors to actually come up with a value that is from actually this plus to minus for a given system model that we hand into this. This is, of course, based on our, let's say, data set. Yeah? So if you could, of course, calibrate this by running your own system also through this analysis and calibrating the whole data set to your own system. But I think that for most similar systems, it should perform decently well. Okay, now coming to the last part of our approach. So we thought now that we have this conformance assessment, which is very nice and gives you an overview and have also a nice value to say this is good and this is bad. It would also be nice to have an approach for fixing conformance violations and suggesting fixes. That's the last part of the approach. We did this only for certain microservice patterns. In this case, we have, for instance, some examples here in the background of persistent data storage of service interconnections and dependencies through shared services. And the first thing we do usually is to identify and detect possible violations of the conformance. So actually we go through the patterns in here and the best practices that we have found and see what are possible violations that are described in this pattern. And they are enlisted here for these examples. No? So what have been described in the literature. So for instance, here, services have a shared database, but no data is shared via the shared database is a violation, or services have a shared database and data is shared via the shared database. These are two different situations. Why? Because if actually the database is shared, but no data is shared in it between the services, then it's much easier to break them apart than if actually data is shared. So this is interesting to identify. But apart from this, you see that this is actually one very similar violation. So now we go in the same way through all these situations and think about what are in the literature and in our own experience possible fixes for this problem, and what could be a fix algorithm for these things. This is just described here in this table in the background. You don't need to study in detail, but just let us look at one example here, like the first one. So we could not fix the violation, of course. That's always the option number one, because at the end of the day, the architect needs to decide, do we want to do this or not? No? So maybe there's a reason for sharing in the database. And we don't want to fix it. No? So, and then you can mark it as an exception and just leave it. No? So to give an example, one service that we have seen in one of the systems that I mentioned has a shared database for zip codes. So this has no problem with, let's say, any data inconsistencies. It makes sense to share this. There was this Redis database that does nothing else. Why not share it? No? So this you could mark as an exception. Something else is then introduce new service-specific database and migrate the database access. That's one option. Or we merge the two services with shared database into a single service using just one database. So these are the two possible fixes for this problem, and we can select either one of them. And then what we actually do is we go exhaustively through the tree of all the possible options and always count up the new options. And with this, for instance, here in one of our systems, which is TH1, so it's so-called taxi hailing service, that's why it's called TH1, you can see that you go first to one, so there are two violations, yeah? And either I can go this route here, and actually these things that are outlined in with a bold line are things that fix all the violations that we have seen. Yeah? So obviously here you have an option to directly go through this fix, and you also fix the other violation by accident. Yeah? So that's interesting to know. No? So you can show these possible fixes, but you can also go to all these other fixes, but then this other violation is still there, and there are still a couple of things that are violated. And a couple of them actually lead to a new violation. And again, we come up with a situation that actually, yeah. So the interesting thing here is as an architect, you get all options how you could refactor your model in order to come up to a solution that actually is then a fixed solution. Yeah, and with this you have then also the fixed options in this project. And here the idea is that we put this also in the CI/CD pipeline, like a manual gate in the CI/CD pipeline, that you have the architecture assessment and you calculate your metrics. And if there are violation found, you suggest the fixes. That's down here. And the architect can then select fixes. You suggest the architectural factoring, calculate the metrics again until at the end of the day you are happy with the fixes you are employed. Yeah? And very likely then in the future it's not so likely to come up you come up with such a problem again. No? So in conclusion, we have suggested an approach to systematically study the architectural knowledge in numerous subfields of microservice architectures, much in the same spirit that the pattern community has, yeah, so that you somehow also like the empirical software engineering community, so that actually you reverse a bit the idea of only innovating in computer science, but also looking at what the practitioners actually do, what is successful, what is not so successful in practice, and developing measures for it and things like that. Then you go to applying this in open source systems or other things. In our case, we were lucky that there are many open source systems that we could use. They are not so large, but we could verify that they actually use the practices that are common in modern systems. And they were all built by practitioners. Yeah? So they this robot shop system that we have seen is built by the people from the company Instana. Because they want a demonstration system for their technology. Yeah? So they employed all technologies that they have seen at their customers. And for security, obviously, they didn't care so much, as you have seen. But others were specifically demonstrations for security practices. So that is also interesting. Then the model extraction from the code, which is an optional step, but sometimes needed. And then you need it if you want to work on a code repository. And then last step, which was the biggest part of this presentation, is actually the approach for getting detectors and metrics. So detectors show only violations. Metrics show you an aggregated picture, but only of one property. And then you can go one step further, having these regression models to actually then have an analysis of one property. But this needs interpretation of the statistics, and of course then the detection strategies with their specific suggestion can be actually more helpful. And if you have such violations, we also suggested an approach for fixing these things. Yeah? So these are the main steps, and that would also conclude my talk for today.
Thank you very much for your keynote. Now we have some time for questions. We have, I think, some 5 minutes for recorded questions, and we can prolong this for a bit more because this keynote is recorded. So the most important questions first. But I'm joking, don't hesitate to ask anything.
If no one is asking, then I can ask. Did you consider maybe by doing this research part of knowledge management, including this research, like how you're going to manage the knowledge, as you mentioned, when new colleagues come to the society of developing and doing this stuff? Do you maybe have the idea how you're going to implement the process or idea for this?
To be frank, not specifically in this approach, but of course the area that I have explained first is called architectural knowledge management, yeah? Because you want to manage the knowledge of architecture in your company. So we actually assume that the architectural decisions are used to actually document the core knowledge. In practice, often done by other techniques than in the ideal academic space. Many, of course, use templates in Markdown and things like that, but it is done in practice already to a large extent. So then it's usually close to the source code, which we would also recommend. Our contribution here goes more in the direction that we try to help with the reusable architectural knowledge, so knowledge that transcends from one project to the next. Yeah, and these are reusable so I didn't explain this in detail, but let's say if you document the architecture decisions in one project, it is essentially the architecture decision of this specific project. And the ones I mentioned are things that you could use across projects. And this abstraction we as scientists do, but in practice this is rarely done. And I would recommend to have this two-stage approach, especially in companies where you have recurring architectural decisions. Let's say a big company builds service-based factories with IoT for their customers. Let's say, as an example, if they do this over and over again, then it of course makes sense to take the knowledge from one project to the other and document it for that company, as an example. So in such if you have just one project, then just document it in the concrete cases. No?
Of course. What do you think about maybe using some kind of workshops to minimize, because this what you mentioned and presented is quite broad and it's a very huge knowledge to process. What do you think about maybe some small workshops like this kind of seminars or lectures where the new employees would be able to process the knowledge in small details, small chunks of the units which they are able to process and to follow?
Yeah, makes a lot of sense. Let's say, just to say what I have explained today, of course, is the approach from the perspective of the science behind it. Yeah. So as a user, you don't need to look at all these details. So you don't need to understand how the regression models work.
Then in that case, you want to say that, if I understood correctly, that this could be divided in a way on architects, developers, and also business people, managers, which are able to process or follow the process of developing the stuff in CI/CD pipeline and everything that they have in this.
Yeah, if you have these roles, no, so some companies don't have these roles anymore, but then maybe somebody on the team is interested in these values, but then you have only a small scale setting. But there are also settings in this world where, let's say, an architect has to process the CI/CD pipelines of a lot of projects, and then you don't get the...
That's the main reason why I'm mentioning this.
Example, you have in a company you have an API team, and the API team is responsible for the APIs of all your company, and you have 150 APIs or something like this as an example. Yeah, what do you do? The API team cannot review all the CI/CD pipelines, no? But they need to give feedback to all of them, and they wouldn't like to know where do we stand. No? And they would like to have a portal very often than to have such values, no? and numbers. No? But this is only applicable for larger companies. No? So for the smaller ones, it's more applicable in a small scale.
Thank you. That is all from my side.
Okay, thank you. This was all for the recorded questions. So you can ask now anything you want. It won't be recorded.